Hi, Karen. Welcome to my very first Instagram Live. Just going to wait a couple minutes here for folks to join us before we get started. If you hear barking in the background, that's probably Nessa. All right, do you have your multimeter handy? Awesome. All right. I know we'll have some folks joining us shortly. So, Nessa wanted to introduce herself first. Well, hopefully with my headset on, you can't hear her too much. So my name is Shannon Donovan. I am a teacher in Rhode Island at Scituate High School, where I have had a need club for 16 years now. I teach science and engineering, and more recently, I am the STEAM coordinator and the CTE coordinator at Scituate. And I've been doing stuff with need since my second year of teaching. I got involved because a postcard showed up in my mailbox about a workshop that was going to happen at a middle school near us. And I asked permission to go. It was the first time I went on a professional development workshop at school because I was very new to the group. And I went to Parkview Middle School and participated in a workshop that was entirely led by students. And I had a fantastic time. And afterwards, I had brought two students with me to that workshop. And afterwards, they after seeing all those students give that workshop, they were like, we could do something like that, right? Why can't we start a club? So we did. And I've been bringing kids to Need Youth Awards in Washington, D.C. ever since. And it's been one of the most meaningful things in my teaching career is my involvement with the Need Project and building this extended family of teachers around the country that love to do cool energy projects just like I do. So thank you all for joining us for my first Instagram Live broadcast from my living room here in little old Rhode Island up in New England. We actually have a beautiful day today. We've had kind of a chilly spring. So I'm really excited to be with you. Now, the activity that I'm going to do with you today is from our Science of Energy kit, Station 5, which is about transformations of chemical potential energy into other forms of energy. Part of that kit has our light sticks that looks at the transformation of chemical potential energy into radiant energy. And we also have the Apple battery activity, which involves transformation of chemical potential energy into electrical energy. So I hope you have had a chance to gather some materials that you have around your house. Now, I was practicing a little bit before because I wanted to do a good job at this. And the apples that we have from the last time we shopped for apples at the grocery store, that was a while ago, are kind of shriveled up and dried. So I'm not actually going to use the apple that I have for my Apple battery demonstration today. Instead, I'm going to use a little bit of orange juice for one of my trials, and I'm going to use a little bit of lemon juice for my trials. The apple, or the juice inside the apple, or the orange juice or the lemon juice, whatever that liquidy substance is, that is the part of the battery known as the electrolyte. So batteries have three main parts. You have your cathode, your anode, and your electrolyte. Okay. Now the cathode and the anode are going to be made of metals. Now, why metals? All right. So this may appear backwards to you on your camera, but I'll tell you, so you don't have to read it backwards. It's a periodic table, and the important thing to focus on over here is this little staircase thing, which is normally on the right-hand side of your periodic table, though it might be looking left to you. Everything to the left of the staircase on the periodic table, except little hydrogen up here, are metals. And one of the really important properties of metals is that they are good conductors. Now, why is that? It has to do with where the outermost electrons are in those atoms. Let me back up. So, atoms. the substance that all things are made of, right? There's three main parts of atoms. You have your protons, your neutrons, and your electrons. Now the protons, which have a positive charge, along with the neutrons, which have no charge, they're neutral, neutrons are neutral, those are located in the nucleus. That's where the bulk of the mass of the atoms is in the nucleus. That's this tiny, tiny speck in the center of the atom. The electrons, which have a negative charge and very, very small mass, those exist in orbitals or shells outside the electron. And there's multiple shells depending on the size of the atom and how many electrons they have. Okay? Now, the metals, because of where their outermost electrons are held, the atoms have a harder time holding tightly to them, and sometimes they can flow away. And this is what gives metals that really essential property that we make use of being good electrical conductors, because they don't have a really tight hold on their outermost electron. Whereas these guys over here, the non-metals, they hold on really tightly to their outermost electrons. They don't let them go. In fact, they want, except for the noble gases over here, the rest of them want just a couple more electrons to have a full outer shell, and so that's what gives atoms their properties and causes them to act the way they do with other atoms, is all about the electrons, because that's what's on the outside of the atoms. And so if you're going to interact with somebody, right, they're going to interact with your outsides, not your insides, right? Same thing with atoms in chemistry. It's their outsides that are going to interact, not their insides. Okay, enough about that. Let's get back to this battery thing. So batteries, three parts: anode, cathode, and electrolyte. So now, if you've done this in school before with your teacher using some of the neat materials, you may have seen this. This is a microamp meter. It's a really nice little tool to measure very, very small currents. Now this is micro. So if I have just amps, right? If I have 1 amp, think of that 1.0. If I have a milliamp, that is 1/1000th of an amp. If I have 1 microamp, that is 1/1,000,000th of an amp. So we're talking very small amounts here that I can measure with this. I'm guessing you probably don't have one of these at home. I'd be really impressed if you did. You may have a multimeter at home. If any of you folks do any kind of electrical work or electronics work, you probably have a multimeter. It's a handy tool. You've hopefully used these at school, maybe not. Now, just a couple things about electricity. This is called a multimeter because it can measure multiple things. What are some things about electricity that we can measure? We can measure voltage, we can measure current, and we can measure resistance. These three parameters are related to each other by something called Ohm's law. We're not going to get into that, but if you like doing math, which I like to do, you can do some fun things with Ohm's law and calculations related to electricity. Your multimeter will also let you measure continuity, whether a circuit is closed or complete. Okay, so a circuit is a path through which electrons can flow. If the circle or the circuit is complete, the electrons can flow. If it is open, they can't flow. Okay, and so let's see, what am I going to use here? I have a piece of copper wire that I had because I had my need kit. Now, if you don't have copper wire, what could you substitute? What's something you probably have hanging around your house that could substitute for a wire that's made of copper? Maybe a penny. So pennies, and here's just a little aside for another experiment you can do later if you want. Pennies have a coating on the outside of copper, right? That gives them that shiny, coppery color. But copper is very expensive, right? If we had to make pennies out of solid copper, they would actually be worth more than a cent because of the price of copper now. Interesting tidbit. Now, over time, the U.S. Mint changed the amount of copper that they put into pennies. What is the rest of the penny then if it's not copper? Good question. On the inside is zinc. So it's actually zinc that is coated in copper. And over time, the amount of copper has gone down. So you could do a cool experiment collecting pennies over a time period and, look at the date on the on the pennies to see when they were made, and then you could actually calculate the density of them and look at how the density of pennies has changed over time to get an idea of how the amount of copper in the pennies has changed over time, because copper is way more dense than zinc. But anyway, that's a fun experiment for later that you can do. So if you need a source of copper to do this experiment, you can try pennies. Now, there's a difference between these two, right? There's a lot more surface area on my long stretched out piece of copper than there is this. So you might not get this to act the same way as my piece of copper. And then I'm going to use a nail. Now, nails are steel, right? That's going to have iron in it. But to avoid rusting, most nails are galvanized. They're coated with a layer of zinc to reduce the rate at which these things fall apart, rust, and are no longer fastening whatever they're supposed to hold in place. Okay, so these are going to be my electrodes, all right? And I have my handy dandy alligator clips. The color of the alligator clip doesn't matter. This is just a conductor to help us complete our circuit. Okay, and I've got my OJ. I'm going to start off with my OJ, and I'm going to put that in there. I'm going to use a piece of tape just to hold the copper rod to the side of the glass so it doesn't tip over on me. I especially don't want my electrodes to touch inside the battery. Any ideas out there why we wouldn't want the copper and the zinc to touch inside the battery? Any of my listeners want to make a guess? No? Okay. Well, I'll do a little experiment here in a second, and you might get a better idea about why I don't want those to touch inside the electrolyte solution. All right. So I have taped my two electrodes there. They're in the OJ. I've got to get my second alligator clip over here. All right, I'm going to set that down. I need like 4 more hands. Maybe Nessa will come back and help me. Nessa is my Great Pyrenees, my office mate during COVID. All right, so let's see. Where can I set this down so you can see it? Oh, no. That was exciting. There goes my lemon juice. Oh, well, I might not get to do that trial. That's okay. Oh, it smells lovely, though. All right, don't go anywhere. Stay there. Okay. All right, electrodes. Okay. Now, as I was saying with my multimeter earlier, we can measure several things. What I'm going to measure is the amps, the current. Amps is a measure of current. Now, I don't know if you can see on there, but amps is over here. And you notice there's a straight line and there's a dotted line. So the multimeter can be useful with both direct current and alternating current. Does anybody know what we're dealing with a battery like this, whether it's direct or alternating? Any guesses? It is direct. And so that is represented by the solid line on your multimeter. Okay, so I am going to be measuring very, very small amounts. So when I turn on my multimeter, I'm going to turn it all the way down here to where it says 200 M. So that's going to be a max reading of 200 milliamps. Okay, so there we go. And I have a very small current. I don't know if you can see that. I have 0.1 milliamps. Now, just to show you, for comparison's sake, I want to show you what it would look like if I used my handy dandy microamp meter from Need, which I love. Okay, can you see this? All right, so over there, and let me screw that on a little bit more. Over there. Oh, Now what happened? Did you notice what happened there? Let me unplug it. Watch the needle. See the needle? Okay, so there's a closed circuit, and now this is an open circuit. Did you see what direction it moved in? Now, if I want it to move in the other direction, what do I need to do? Okay, I'm going to switch the leads here. Let's switch this one over here and switch this one over here. And now you can see the needle went back in the other direction. I don't have a good grip on that. So that just means what? That the electrons are flowing in the opposite direction. All right, I'm going to take what's left of my lemon juice after I spilled most of it on my lap and add it to my orange juice because I want you to see what happens to my current. Can you see it? I have a very small current. I'm adding my lemon juice. And it didn't change. Do I not have a good connection here? Let's see. Never fails. This worked before when I practiced. Yeah, I didn't have a good closed circuit there. My alligator clip was more on the plastic than on the metal pole. There we go. Oh, look at it now. It's off scale, off the charts, way over here. All right, so see how it went back? All right, let's go back to the multimeter now. It really liked that lemon juice as the electrolyte. So let's go back to this. Now, okay, we made some electricity with our fruit juice and our anode and our cathode. Cool. Is that useful? Well, if I were to add additional cells, you could consider this as one cell for my battery. You know how a lot of devices that you use have multiple batteries in them joined in a series or a parallel circuit, depending on what the needs of the device are. You could do the same thing. Now, I don't want to spill any more lemon juice in my lap, so I'm not going to do this for you right now, but here's a challenge for you to do this at home. If you have something like this called an LED, a light emitting diode, I bet if you made several cells like my lemon orange juice battery here and arrange them in a circuit, I bet you could figure out how to light this. Now, how would we do that? Well, if I had my other jar here, let's pretend I still have lemon juice in my other jar, and I happen to have another piece of copper, and I happen to have another nail, right? And if I have another set of alligator clips, I can set up a number of batteries in a circuit and add the current together to push more electrons through that device and try it lighting it up. So you can do a number of experiments if you have these things. So again, we were going to do an experiment that we mentioned earlier about having my electrodes touch. So you see I have a current right now in my orange lemon juice battery. And what I'm going to do is I'm going to touch the nail to the copper inside the battery, and I want you to see what happens to the current. I have to undo my tape that I did up before to prevent this. Definitely need more hands for this. I'll have to 3D print one. That's what's behind me over there is my 3D printer. I've been printing ear savers for the last 8 weeks for some of our friends working in the healthcare industry. Anyway, so, all right, so we have our current, our battery going, and then I touch the copper and the zinc, and I have no current anymore. That's because what I've done is to create a short circuit in my battery. So now, instead of flowing through the wire and through my multimeter, the electrons are flowing directly from one of the metals to the other. Now, in addition to doing some different additional batteries and connecting them in a series or parallel circuit, we could also test some other parameters. You could test some things like surface area. So if I have a long skinny wire like this, and say I wind it into a coil so that I have lots, if I have a longer piece of this and I wind it into a coil, I have lots and lots of surface area, and I connect that to my alligator clips instead of just the thick copper wire. What impact is that going to have on my current? I'll let you experiment with that. What about other types of metals? What other metals could you try? Do you have something at home made of brass? Do you have something made of nickel? Now, you'd want to try to make some predictions before you do these tests, right? And if you want to dig in deep to this, you want to look up something called the action potential of metals. So we said characteristics of metals is that those outermost electrons are loosely held. Some metals, some elements hold them more loosely than others. And the amount that they pull on electrons towards themselves is a characteristic of those metals. And so if you look up the action potential of electrons, or the activity series, if you Google activity series of metals, you'll be able to get a nice list that'll allow you to make some really good predictions about how much a metal is going to pull on electrons, and potentially pull the electrons towards it, causing a flow through a circuit. So I hope that was helpful. I don't want to go over time too much. I do this safely at home. Remember, if you want to try to light an LED, you can take multiple batteries and join them in series. I don't think I finished telling you how to do that, right? So if I have, say, this red wire coming from the nail in one of my cells, and I have a new cell in another piece of fruit, or in my case, a jar. Okay, so I have one lead going to the copper, then a lead going from the nail to the copper in the next one, and I don't have any electrolyte in this one, so it's not going to be a complete circuit, so we're not going to get flow, right? And then I have my LED. Now, LEDs only work in one direction, so if you don't get it to light up with the legs of the LED clipped on in one orientation, flip it and try the other orientation. And to understand why that is, you can Google LEDs. All right, and then I will complete the circuit. And it's not lighting up because I don't have any electrolyte in this battery. It's an empty battery. All right, so you try it out, you experiment at home, and let us know what you figure out. I hope this was helpful, and we'll see you on the NEED website soon. Bye.